So we have previously seen a hyperboloid of one sheet, and now we're going to look at what happens when you have a hyperboloid of two sheets. And in a one sheet equation, there was only one negative term present. In a two sheet equation, we get two negative terms, and so that is the distinction. Once you have put your equation in standard form, you'll see that all of your variables are squared. The equation is equal to 1, and when you make sure that the equation is equal to 1, you end up with two negative terms. And whatever your positive variable is ends up being your axis. In the hyperboloid of one sheet case, whatever your negative term was your axis. If you wanted to put this into context where you think of one rule that works for both a hyperboloid of one sheet and for two sheets, you could think whichever variable has a different sign from the other two. So in this case, there was only one negative, so the variable with a different sign was the negative variable, that became the axis. When I come down here, this time the variable with a different sign is the positive variable, that's the axis on which I'm opening. And the shift that you see, notice in the graph, this is shifted up to C and down to negative C. That comes from whatever the coefficient is in the coefficient of that positive variable axis. So the shift equals the positive variable coefficient. So I've already drawn the picture, but we're going to go through and make sense of the traces. So remember that a trace is what happens when you essentially set one of the variables equal to a constant. Usually we think about traces in the coordinate plane, so usually we set one variable equal to the constant 0 and then investigate what happens from there. So in the xy plane, I have set I have set z equal to 0. So I'm asking myself, what am I going to see if I were to slice my quadric surface at z equals 0? And if you come over to this graph, you notice that there is no graph between plus and minus c. So there's no graph for z strictly between plus and minus c, so negative c less than z less than c. What that tells me is that I'm expecting that when I go to look at traces, when I set z equal to 0, for example, I shouldn't have any kind of solution to my equation because there's no graph there. To make sense of why I would expect to not have a solution to my equation, I'm going to come over here and take a look at this term. When I set z equal to 0, what I'm left with is the sum of two negative squares. When you square something, we know that it's greater than or equal to 0. So if you attach a minus sign to it, this quantity that I have boxed in is always less than or equal to 0 at the largest that it can possibly be. It's 0. So there's absolutely no way that it's going to be equal to 1. That tells me that there is no solution when I look in the xy plane. But I could pick other values of c and sub those into my equation and see what I would get when I fix different heights to look at. Instead of looking at just, the floor of my coordinate system, z equals 0, I could shift up and I could look at, for example, z equals c. If I look at z equals c, so I'll go ahead and write that here, then that would be what I would get if I sub in z for c instead, and I'm going to get negative x squared over a squared minus y squared over b squared plus c squared over c squared equals 1. Give myself some more space. Notice that this term is equal to 1. So now I'm at the point where if I were to put this all on one side, I would have negative x squared over a squared minus y squared over b squared equals 0. And there is a solution to that. The solution to that is when x and y are both 0. And so what we get is an actual, just a single point, and that single point that we get is that vertex that of the hyperboloid of that top sheet at z equals c. And so here we're getting a point, and the point has coordinates 0, 0, c. The reason we know that the z coordinate is c is because we fixed it. Now, if I had put in plus or minus c, I would have gotten the same result, because z, like if I put in a negative c, z is just squared and I get the same equation. So I could go back and say, let's call this trace z equals plus or minus c instead, and then what I would see would be I would get a point. It's just that the point's z coordinate is either going to be positive c or negative c. So I could write this as 0, 0, plus or minus c. And then that would pick up both vertices. Now, the reason why I skipped straight to looking at c is because we just found out in the previous, like when we were looking at this box, this term is always less than or equal to 0. So we're going to be relying on adding something to this side to bump this number up high enough so that we can get to 1. I've got something here less than or equal to 0. I'm going to add something to it, and it's got to get me to 1. The only way that's going to happen is if this term is at least 1, because this only serves to make z squared over c squared smaller, since x squared and y squared are positive and their subtraction would be less than or equal to 0. So that tells me that z has to be at least c or negative c before it's possible to add something less than or equal to 0 to something, that I get from z squared over c squared and get up to the value 1. Now, I could go higher than that. I could look at, say, z equals plus or minus 2c. And if I do that, what I will end up with is an equation that looks like negative x squared over a squared minus y squared over b squared. And then I'm going to get plus, and I'm subbing in plus or minus 2c for z, and so that will give me 4, this will end up being plus 4. If I sub this in, if I sub in 2c there, I'm going to get 4c squared, but that'll cancel with the denominator, and then that is equal to 1. But I could solve this, and I could say, I could take that 4 to the other side. If I took the 4 to the other side, this would become a negative 3. Then I could multiply through by a negative, and what I end up with is an equation that looks like an ellipse. And so in this case, I get an ellipse. And that is what we were expecting to see based on if I came up here and I thought of this as being the value 2c on the graph, I would see an ellipse, for example. And same thing down here at negative 2c, I would see an ellipse. So then what we need to do, and just to add to the picture here, there's no graph for negative c less than z less than c because there's no solution. Because traces have no solution for these values. to check out what's going on in the YZ plane and the XZ plane. Luckily, things are pretty normal there. In the YZ plane, that's when x is 0, so I'm going to end up removing this term. What remains is going to be the equation of a hyperbola. So remember, when you're figuring out, well, what axis are these opening on? It's the positive variable, so these are going to be hyperbolas on the z. And when you have hyperbolas on an axis, you open according to its coefficient. And so that's why we're ending up seeing, these kind of look like parabolas in this picture, but they're actually hyperbolas. So if I wanted to highlight, what these hyperbolas look like in the YZ plane, that's where this hyperbola is coming from here. And then similarly, if I go in the XZ plane and I cancel out, I remove y from the equation, then I'm going to get hyperbolas on z as well, because z is still positive. And so I might, let's make this red or something. We're going to get hyperbolas on the z, and that's coming from hyperbolas in the xz plane, which is what these are here. Notice that those are shifted like they're parallel to the xz axis. And so that's our shape.